Welcome back, everyone. That's important. So let's keep going with our course. Just as a reminder, there's a Slido. If you have questions, I'll check it maybe every now and then. And then, yeah, you were here yesterday, so we don't really need much introduction. We had talked about basics yesterday, so today we can jump right into it. We set up an optimization problem and solve it. And we'll keep solving this problem for the next 3 or so lectures. So if you think about optimization, especially in the context of machine learning, it has like a bit of a different taste from optimization you sometimes hear in your usual comp math classes. So maybe good to keep a reminder that this optimization actually they started really working on stochastic methods all the way back through the 50s, probably more out of necessity with limited compute and so on. But sort of the really big revolutions in terms of machine learning happened then when people figured out the backpropagation, basically the chain rule, applied it to neural networks in about the 80s. And then today, most of the work that is still happening in that area is about acceleration and implicit regularization in these stochastic methods. And the problem is inherently stochastic, the way we set it up. We want to minimize some expected loss function. And then the choice of algorithms that are commonly used today reflects that to a certain degree. But I will contrast this also with a classical viewpoint that you may know. So we'll talk a little bit about a little lecture outline here in the bottom that we'll go over. So we'll learn all of these acronyms, we'll talk a bit about backprop and automatic differentiation. Then we'll find an old favorite relative of ours, the Gauss-Newton method. And then we talk a bit about SGP. That's the plan for the first lecture, and then the second lecture we'll look a little bit more under the hood. Okay, so key question is, how do people train neural networks when you have millions or billions of parameters? And I think one of the things that we learn typically is that this must be some gradient-based optimization because anything else would not scale in that high dimensional spaces, but then what? So the four sort of steps that we're going to do is we're going to distinguish between stochastic approximation and then stochastic average or sample average approximation, and SAA. This is sort of a common division of the whole landscape of stochastic optimization that is good to be knowledgeable about when you work in this area so that you know which side of this you're on, because depending where you are, you have different theoretical things you need to study and also different algorithms that you're using. So it's good to clearly separate them first. Then again, I'll show you some way how to get gradients efficiently. Then we'll talk about Gauss and Newton, because that is sort of a very common mathematical tool that we're using for usually least squares, fitting nonlinear least squares, but also you can carry it over to more non-convex, or no, sorry, convex loss functions, which I will show you how to do that. And sort of this is a prototypical computational math method. Let's just see how it does for machine learning problems, and then maybe also seeing why it's not what DeepMind and Meta and others are using today, but would like to move to that direction. And then later on, we'll go to a much simpler method, which is called stochastic gradient descent, which is the prototypical stochastic approximation method, and try it out, take it apart, and see how that goes so that we can see kind of what is the difference between these two different regimes. We have a running example. This is one of my favorite. This is called the peaks problem. So MATLAB has this 2D peaks function. It's just some weird function that has valleys and hills, and you can make a classification problem out of this, which I did by just picking level sets. So you see these different colors. These are different class labels. So we talk about classification in this class exclusively. And every point is sort of put into one class based on sort of the height on the surface of this function. Okay. And what I like about it, it's a 2D example, so we can actually see the whole thing. It's not high dimensional excuses or so. Everything is there for you if you want to check it out. It is quite complicated to think about how to fit the classifier to this, because you have regions that are not connected, like this green one here scattered. You have this little pocket here in the middle that is going to give us a hard time. So it's not an easy problem, even though it's just two-dimensional. Okay. We're keeping the architecture simple, so we go basically for our baseline architecture, just one ReLU layer and one layer that maps us back to the 5 classes, and then we take a softmax. Okay, and this is again getting into probability spaces if we want to. And we have a simple cross entropy loss function, which we've seen yesterday toward the end. So log sum x, that's a convex function in F, but not so much in the parameters. And we're going to start very small. We'll pick like, and I think we have 800 data points we're going to use in training. We have 200 weights, very small model, okay? Nothing fancy. And then the goal for the first part of it is, okay, how do we find sort of theta star, the best weights that we can find, and also what do we mean by best weights? We should chat about that. Okay, so that's like a running example. Hopefully that makes sense. By the way, I uploaded the codes for this on GitHub, so you can play with all of these things on your own time and tell me what you learned. But that's sort of a very simple problem. And universal approximation theory is on our side. If we make this thing wide enough, we know that we can fit everything. Okay, go. So there are two ways to minimize an expected loss. There is sort of the sample average approximation and the stochastic approximation. So let's just see what they do. So in SAA on the left, what you have is you're minimizing, so you're approximating the expected value with an average, a sample average. That's why it's called that way. And then you forget about the stochasticity. At least for a while, every now and then you may go back to it. Okay? So when you look at this problem here, this is a perfectly fine optimization problem that you see in an undergraduate class on numerical optimization or nonlinear optimization. However, on the SA side, what you do is you really try to find a minimizer of the expected loss. And why are they different? So think about like a data set that is infinite in size, where you can sample infinitely many data points, if you will, which for the peaks function we could actually. You're never going to really compute the expected value. And now the question is, how do you minimize something where you cannot even evaluate the loss function? But this is really the contrast. On the left-hand side, you have everything in your hands. On the right-hand side, not so much. You need to have theory on your back. Okay, so then in terms of algorithms, on the left-hand side, you may think about whatever your favorite deterministic optimization method is. For me, they always look like so. So you have some update with some matrix inverse and some gradient, okay? But whatever you want, there's a step here, this eta. You use a line search, use a trust region. It's not a religious argument here, what you want to pick. Oh, yeah.
What is second? On the essay, what is expectation?
This expectation is over the training data. It is, but you have a fixed sample. So you pick a big sample, then you approximate this, and whatever you get as a finite sample approximation, that's what you optimize. On the right-hand side, actually what you'll see is whenever you evaluate a gradient, you'll get a new sample, IID. So the data set is not fixed.
You have so much data. So you divide
yeah, if you have a lot of data on the right hand side, maybe you will actually in the prototypical algorithm you will just look at one sample at a time, whereas on the left hand side you'll take the full batch. Yeah. Okay, so that's sort of the rules of the game. And then yeah, this one here is actually simpler. It doesn't have a matrix inverse, but most importantly, it has this eta t, which is what we call a learning rate or step size. And you use your best judgment and maybe some good luck to find it. If you satisfy two conditions, so on the left, I mean basically like the classical statistical learning theory is how you analyze the problem. So basically you find out how close is my average approximation to the actual thing. If it's close enough, then the minimizer of the thing you optimize should be good for the other one too. This is second. And then on the right-hand side, what you need is you need to make sure that this estimate of the expected gradient is unbiased, which it will be if you have IID samples. And then you have to have a suitable choice of your learning rate. And then you can show convergence. We'll look a little bit more into details of this. Sorry? No. There are some rules. We'll get to some rules. And yeah, advantages, I mean, on the left, I think one thing I would like here is like we have very well understood methods. They are not really parameters like a learning rate, whether we need to tune. And also, it's very good for parallel computing because you have a large batch. You can do this all in parallel. Whereas on the left-hand side, you have like tiny updates, and you need to work a little bit harder. However, on the right, what you will see is actually, I mean, it doesn't get any simpler than that. Okay, if you're happy to tune this eta and fiddle around with it, you need to take a gradient, which automatic differentiation will do for you, and then you go. And the the rumor on the streets is that this will actually generalize, which we'll see later. That was one more question if we can.
Yeah, so these theories are 47 years apart. Is there some relationship between them historically?
Not really, I think. I mean, there's like, well, I mean, they meet sort of in the current era. Like people are not so clear about one or the other, and then actually they're segues. I don't think so, really. I mean, like, these are pretty much divided approaches. You pick one or the other. It gets a bit more muddy when you have mini batches. When you have a mini batch SGD, so in practice, what you would do is you would actually have a second parameter, which is called the batch size, and then you pick a few samples at a time to do a gradient estimate. And this you can look into two ways. So you could look at this in a SGD sense, where you now have a better, like less noisy estimate of your gradient, or you could look at this in an SAA view if you have really large batches that you sort of do one step for a large batch and then resample. But that's in practice what you do. I think usually you should just look at the size of B to see if you're closer to SA or closer to SAA. And in most machine learning, you're very close to SA. You have like 16 examples or something like that if you have trillions of tokens. Yeah, and B is a batch size, so this will come up. Other key terms in when I say something like an epoch, that means if you have passed through all of the finite training data once, that's roughly comparable to doing a step of gradient descent on the SAA. And yeah, otherwise an iteration would just be like one step. And yeah, so on. We'll go back to this. Okay, so computing gradients is important because clearly these models have millions to trillions of weights. And you cannot use finite differences. Okay, everyone will believe that. So the solution is called backpropagation or automatic differentiation. Basically, what you do is you evaluate your loss function, which is just a scalar, and then you backward walk through the computational graph to compute the gradient, all parameters at once. So you go forward through your network and backward, and then you have it. This is how sort of it looks like in pictures. So you have your input feature X at the bottom, and then you go up to evaluate your loss. So this is just a number like 1.3 or something like that. And then you go backward through the whole graph and apply chain rule. It's really like a chain rule example you see in an advanced calculus class, but with a actually chain graph. So there's no different trees and branches. Okay. And this is done in software for you. So if you have PyTorch or JAX or TensorFlow, this is sort of set up to do these operations for you. They automate the graph construction. They have built in, this is called reverse mode automatic differentiation because you go backward from the loss to the inputs. Usually you also want to look for a forward mode sometimes, which you could use if you had a function with few inputs but many outputs. Then it would be more efficient, but mostly in machine learning 101, you just use that. There are differences in the implementations, but that is not really important too much for this course. And yeah, this technology has become actually quite good at also handling complex control flows and so on. So it's a really enabling technology because some of these network architecture, we had this messy picture of a transformer architecture yesterday that look completely, I mean, you can break it down and you can compute a gradient by hand. It's nothing wrong about it. It will be as efficient in terms of compute, but it'll take you a day or so to do that and to test it. So this is a foolproof way in most cases. If you have never wrestled with that, this is sort of how this could look like. You define just a loss function, and then you can call for something like a value and a gradient of the loss function quite easily. And then you have it, and then you can so you do your SGD step. So you have your parameters minus the learning rate times the gradient. Easy. Okay. And yeah, today, I mean, I'll show you some JAX code because that's what I used for the notebook. They have a quite nice way to do automatic differentiation. Good. Gauss-Newton. So this is an SAA method. And it's not maybe the most mainstream thing that you find in a machine learning course, but I thought since it's a computational audience, we should start with that. So what does it mean to use Gauss-Newton, which is the nonlinear least squares optimization method, to the softmax problem, which remember is not a least squares, it's a log sum x. So what we do is we have the per sample loss. So that's f theta of x comma y. Your y is your actual label, and f theta of x is the prediction of a network, but is not in logits yet. That is like the common thing when you work with a softmax. You don't do the logits there. That's handled separately because we saw the log sum x has a very nice Hessian, diag p minus pp transpose. So we'll capture that. So for Gauss-Newton, the general playbook is you need to linearize something. And in this case, we linearize our prediction function. So we have the f theta of x linearized about theta 0, current guess. And this J is the Jacobian matrix. Can someone tell me what size this will have roundabout? Someone who grabbed their certificate already? Yeah, or have a wild guess.
I mean, it's on the board.
Huh?
You have it on the board.
Yeah, but what was NMP, MNP, roughly? If you followed along with the peaks example. Yeah, 261, I think, was a P. It's very good. And M was, how many colors did you saw on the peaks? 5, yeah? So it's 5 by 261 or something like that. Good. Very good. 2 people have already earned their credits. And then this is per sample, right? So and now for the actual problem, you will have big N of those. So that'll come in handy. Okay, good. So now what you have actually at this point already, so maybe more advanced question. So now we have linearized our neural network about this point. And now if we look at it as a function in theta, we already have a convex program, right? Log sum x this program as is convex. Concatenation with an affine function preserves convexity. So you already have a convex program there. But we'll take it one step further. We'll actually do a quadratic approximation because that's usually what people do in Gauss-Newton. And what happens there is that now you plug in the linearization into the loss function and then use a second order derivative of sorry, this h sub I is actually the second order derivative of this loss function. So this matrix, as we just figured, is a 5 by 5 matrix, diag p minus pp transpose. Easy to get. So that means that you can sum this over all of the data points and probably should put some average around it. And there you have an approximation to a Hessian matrix, and you could use that in your algorithm to scale the step size. So this is what I mean by a Gauss-Newton method for softmax problem or for log sum x problem. Okay. So if you have standard least squares loss, then it's really just the J transpose J that you're used to. And for cross entropy loss, you'll have this one.
So it is for theta, this problem.
Excuse me?
Yeah, so it is for theta.
Yes.
But if theta is very far from the theta 0 there.
Yeah, then tough luck. Then you need to make sure that you get closer and you need to make sure you start appropriately. So we'll see. Like all of the general rules about Gauss-Newton, they still apply for machine learning. Right? I mean, you have nice conversions when you're close, and when you're far away, this may be not a good linearization. So anyway, yeah. So that's, of course, all of these standard things will apply. Good. So since we said that we have a very small number of outputs here. Oh, yeah.
Question on the conducting.
Yeah.
So the F here is two-layer ReLU network.
Yes, or whatever it will be, but it's
So the Jacobian there is chain derivative across the two-layer network,
yeah, it'll be a 5 by 261 matrix.
right? But it's multiplication of individual layer derivatives. And there is a nonlinear function in the middle.
Yeah.
How does that affect the convexity?
Oh, it affects the convexity of the actual loss function quite dramatically. This is a non-convex problem, period. But this problem that you linearize is going to be convex because you're replacing. So look at this. I mean, like this approximation of the function is affine in theta.
Okay.
Now you concatenate a convex with an affine.
That's because you basically
Yeah.
bound the region over which you linearize by keeping.
Exactly. Very good. Good. So since we said we have very few number of outputs, I would want to make the claim that we can actually do this and try it out. Generally speaking, this whole Jacobian that you would have, again, would be m times big N, which is very large. But if we just look at one sample, it's a 5 by 261 matrix. So here's my back of the envelope computation. I do 5 backprops, and I have that Jacobian. Well, 5 numbers backward, and we'll get there. And I could do this even for data sets like CFAR10. I have 10 classes, so 10 backprops, and I have the Jacobian, and I hold it in my hands. Sometimes I like to actually see something, so I have it. And it's interesting to think that way because you may think, okay, so now I have to do this, but then I need to do this for all the samples. Sure, we'll do it for all the samples, and we'll do this in parallel, so it'll be actually quite fast. And then you say, okay, so what about memory? Memory is a bit more delicate because, of course, you need to store this matrix, and it's going to be many rows and many columns if you have many weights, but we have few weights, so we don't worry about that. And also, I will say that it's sort of an interesting way to think about it because we said actually yesterday and briefly saw it on the graph. In order to do a backprop, you actually need to save or recompute all of the hidden activations, all of the hidden features. That's also memory, and you need to keep it alive whenever you need to get back to it. So here, after you have computed your little Jacobian, you actually can erase all of the hidden features. So it's a kind of a numbers game, you kind of pick. But I just want to make the case that in this case it's feasible. This is how it looks like in JAX. So you have a Jacobian in reverse mode of this forward function, and this VMAP is just doing it for all of the data points. And it actually turns out to be quite fast. Okay, good. And then it's linear algebra people here. So dense linear algebra on GPUs, that's also a lot of fun stuff that can happen, but it's actually very doable to solve problems of that sort, either directly or iteratively. But yeah, it's sort of, we can do this. So this is what I did. And I'll show you in a second what that went. So here's my cell switch, why I like to do this, even though it's a machine learning course, and usually people think about Gauss-Newton as a waste of time. So theoretically, you have very fast convergence, especially when you think about fitting the training data. That's one of the common things in Gauss-Newton. The term you leave out in your Hessian approximation usually goes down when you have low residuals or when you're about linear. That about linear part, well, I'm not so sure, but definitely we want to nail the training data. So this should be good. Yeah, it adapts to the curvature. It is a fine invariant. So if you rescale your weights, nothing bad happens. The Gauss-Newton part will just take care of that. Otherwise, tough luck. You always need to pick a new learning rate. And I like not having Piper parameters, to be honest. So you just pick your line search or trust region method, and it'll just work the same way. That's the idea. Yeah, and practically also there's a lot of parallelism you can pick because many things can be done in parallel. So this is how it does actually. And when you look at this for the first time, I mean, hard to say if you're impressed or not impressed. So we'll see some comparisons later, but let's just make a few observations. So first of all, you see two curves here just to train our eyes because this will come up a lot more time. So you see iterations. So these are like 30 steps. You see a loss that goes down. It's two losses that go down. One is blue, that's the training loss, and one is little orange or red, that is a test loss. And the way that goes is we train on 800 samples, and the other 200 will look at them only a few times every now and then, but we will not optimize it, not use it for anything. It's not the best setup. You should be more careful, but we can be a little bit careless here. And what you see here actually is this blue versus red is sort of this generalization gap that we hinted at yesterday as well when we did the polynomial fitting. So it does overfit a little bit. there's some accuracy, and you see also here, like in the final accuracy. So yeah, you fit the training data reasonably well. You fit this one reasonably well. Not a bad result, in my opinion. There are a few dots. These red ones here are the ones that are misclassified. They are pretty close to the boundary. So it's not that, you can do Gauss-Newton for these type of problems. It just works, maybe the message. And it's not as, we'll see what the alternative will be. Now, if you think about this through, then if you want to do this for like a ResNet 50 architecture with 25 million weights or so, of course, now I have to give up and need to be more creative. So there you will not be able to store this full Hessian matrix. You will not be able to even compute the Jacobians. So you will not be able to, since you're not going to be able to build it, at least not efficiently, you may be wondering what could you do without building it. So matrix-free ways, people have used them in the past, because automatic differentiation happily computes Jacobian matrix vector products and vice versa for you. But there are a couple of challenges. So first of all, these are expensive, a forward and a backward. That's about another epoch through your training data. So while these methods work, sometimes they're just not competitive to just doing a simple SGD step. And also preconditioning. So I hold the matrix in my hands after I'm doing this for the small example. So I can actually, I pretty much just use a backslash, or I could, if it was too large, I could look at it and quickly come up with a good way to precondition. That is a bit harder when you don't have the matrix. So there's some challenges. But that's where in the literature, Gauss-Newton methods or Newton-type methods, there are a few papers that have been doing this. But at the end of the day, it's really about comparing the cost to stochastic approximation methods, which we'll do in a second, because all of these operations are expensive. But this works. So at least for this one example. Yeah. So now the other thing that you will have is since this is a stochastic optimization problem, we completely ignored the stochasticity, and we sort of got away with it. But there is still this tension, right? So you need large batches to be able to do this. And when you do this, the computational cost just grows and grows. So that's just one of the things. And if you do too small batches, then this Hessian that you get from the Gauss-Newton will just not be very reliable. Generally speaking, you want to approximate that with much less noise than you have coming in from the gradients. So that's then again another different thing. Then the non-convexity, of course, we heard that already coming through. So the neural network is non-convex. So you need to start well. Actually, the Newton direction will always be a descent direction. I should have said it may not be a good one. So then you need things like in my example, I use the trust region scheme, like a little bit of engineering, but it's well understood. Okay, so what we can though learn from it, and we'll get back to this tomorrow in the first lecture, is if you look at modern optimizers, they try to kind of mimic the Gauss-Newton in a stochastic regime. That's also one of the reasons to go a little bit through this. So can you find a cheap and not too noisy way to get a good Hessian? That is sort of what's giving you really the cutting edge research ideas like KFAG and shampoo. But it has to be tractable. And also the inversion has to be tractable, because usually then these operate in a mini batch setting where like I solved 30 linear systems, but an SGD may have 30,000 linear systems that they need to solve. So this also needs to be fast. Okay, so there you want to do structured approximations, which we'll get to a little bit tomorrow. Let's see what the alternative is and talk a little bit about SGD. So we saw that already. So we have expected loss that we're minimizing. We have our SGD update with our learning rate and IID samples that will take, by convention, should be new samples every step. First requirement is that the gradient is unbiased. So when you take an expectation over the data, then you get the gradient of the actual thing. Clearly the case when you have IID samples from your training set. But I should say this is not the only way you can come up with a stochastic approximation scheme. There may be other ways. As long as you get an unbiased gradient estimator, you're fine. And then you have conditions on the step sizes. So the classical ones are as follows. So if you sum them, the sum should be infinity. So you want to be able to move everywhere. You can't decay them too quickly. But then if you sum their squares, that should be bounded. And that is so that you actually converge and that you make sure that you dampen the noise that's coming in from the gradient steps. Because every gradient that you compute here, so this is a noisy estimate of the thing you're optimizing. And that noise needs to be controlled. But then you have some classical results, just to give you a flavor of what you can find, is that if your problem was convex, which ours isn't, then the suboptimality goes to 0 as you optimize. And it depends on a few things. So it depends on the initial suboptimality that goes down 1 over square root of t. The closer you start, the quicker you get there. And then you have some bounds that depend on the smoothness of your problem. And both of them are going to be decaying by design, sort of. And if your problem is non-convex, okay, then you have similar bounds, but they are basically results that you converge to a stationary point. So the norm of the gradient, of the expected gradient, will go to 0 if you keep optimizing, but you don't quite know what you end up with, saddle point or minimizer, which already is a bit troublesome, maybe, that you won't be able to tell. But this is sort of what you expect. I would just remind us that convergence is nice, but it's not the goal. The goal is to get a good model that generalizes to unseen data. So just as a reminder, and these results don't capture that. And what do we mean by generalizing? That will be part of the second lecture today. Like, what do we think we want from a solution, and what can SGD do to get there? Yeah, Andreas?
So in general, I always wondered, since you may say that still, is Newton really worth it in this setting? Because I sort of felt like if go deep quickly, it may actually hinder you to generalize well, just intuitively.
Yes. So is it worth it? Is a very good question, because you need to first know what the alternative is and then do an actual computational accounting for the number of steps. The generalization gap is often quoted as an issue. I would place the Gauss-Newton more in the classical machine learning regime, where you need to worry about your VC dimension and your model size to mitigate that a little bit. So that's where it's one reason why they are not used too much, is that if you scale too much, then they will overfit very quickly. But I think it's still something good to keep in mind, especially if someone finds a good way to regularize the problem. You may be back in business, because you may find a way to regularize, capture really what you want to generalize, and then use a faster method. And for these small problems, honestly, if you want a very small network trained, we'll see what SGD can do. Usually not as much.
I know what loves me the most is the learning rate, and I mean, converge, you get garbage. So.
Yeah, there are ways about that. I'll tell you. But anyway, so that's I think the comparison, right? And if you think about also, it's a good question. You have sometimes a distinction between training time compute and inference time compute. One thing we'll have to do is keep an eye out is when we say we want to over-parameterize things, everything gets more expensive. And you may want, in some especially scientific applications, surrogate modeling or so, you may want to have a small network that you can do inference with relatively quickly. So then, it's a good tool to consider. Okay, very good. We'll chat more about some of these things, but yeah. So a little bit more maybe into some preliminary results we will want to use about SGD is the following. So what happens with batch sizes? So if you have a sort of a large enough batch size, which I admit we will not have, but if you had, then we already saw that the batch gradient would converge to the actual gradient that we would want. But a very common assumption is that due to the central limit theorem, if your batch size is actually large enough, you could think about the noise here the batch gradient actually be almost normally distributed. And that's actually quite a simplifying assumption for the analysis, which is very useful, but it can guide our understanding actually quite a lot. So you have let's say these are really normally distributed, so it will be unbiased, and as you grow the batch size, the noise here will actually go to 0. So that should make sense. Why is that? Because of the IID sampling. So here's a quick derivation. And that sort of also means that the 1 over B is sort of like a noise parameter. And maybe you remember yesterday when we went from the ODE to the SDE, there was also a noise parameter, and the more noise you add, the more bouncy it'll be, and the more diverse our samples will be. So we'll see some similar arguments when we look at the convergence properties of SGD in a little bit to study sort of why SGD may find good or may not find good solutions. But that is sort of one of the common things. I will say that the reality is more complicated. So it's convenient for us to sometimes think about, but just before people get too nervous, empirically, that's not the actual noise is not normally distributed. If you want to do a more accurate picture, then you'll realize that they have heavy tails, and there are generalizations that you could use to describe this S alpha S distributions. So if you have alpha equal to 2, you have a Gaussian, but usually you can reach heavier tails. And yeah, why does it matter? Because the heavy tails mean that you can have large jumps, and maybe for an optimization, that's something you would actually want. So this will come up tomorrow morning when we talk about ADAM and more advanced methods. But sometimes, I mean, it's a good mental model to think about this noise as having some structure, making some assumptions, and then seeing if we can do that. And yeah, just a reminder, a good algorithm converges, but a great one would actually learn. So that's what our goal is. Okay. So how would we see this in action? So this is SGD for our example. And now I don't know what people think about this one. So what do we see? We see mostly it doing quite a good job, but there are definitely a few more red dots everywhere. We see some, yeah. So here maybe also one of the things, if you look at this for the first time, the training loss does not decay monotonically, as you would expect, because I mean, this is not a line search or nothing like a trust region that saves you. There's like some gap, of course, between training and testing. But overall, the gap between training and testing is not what I'm worried about here. Because what I would want to see is, can I actually fit the training data? And it seems like I couldn't. Okay. Now, I need to tell you that this is not just a cherry-picked example. I really try to do an honest effort. So there are tools called Bayesian optimization that you can wrap around this whole training, and I let it crunch for some time. I think I gave it a compute budget of solving this problem a few hundred times and picking different learning rates and batch sizes and decay schedules and all of these things that you don't want to mess with, which used to be called graduate student descent. It's now like a Bayesian optimization, which sounds more humane and is much more time efficient. So this happened, and this is the best I could find. Plus, and the second thing I will say, you do have the notebook, so you can find better ways. But I think what you will find very, very quickly is pretty hard. And this is, I should say, it's like a vanilla SGD. So of course, it's not a serious method, but we'll get to more tricks later tomorrow. And yeah, anyway. Huh? Yes, I don't know. Does anyone remember how Gauss-Newton did? I think that was the training was the loss. Oh,
Not smooth.
in the Gauss-Newton, I think. I mean, I will need to go back to that. We can test that. I don't know. Want to go here, then that. Yeah, let's just do a quick check if I have the units. I see I don't even have the units here, so I don't know quite what it is. But in terms of the accuracy, definitely you see a bump. Okay. Good. Yeah, okay. So now if you well, what to do now, and I think I told you yesterday and kept repeating it, but you can't repeat it often enough, is when you're at this position with your SGD and you don't want to wrestle with Hessian and linear algebra, the safest bet, and that's what all the tech companies are doing with large language models, is to go large. So let's do something obscene. So we have the width parameter here to play with, and we can ramp this up to a number that is much, much bigger than the training set. We have 800 examples in the training set, five pieces of information if you really count them as five. So back of the envelope computations, it's about 4,000. So let's go to 8,000 to be safe. So here's what you do, what you will observe when you go to a very, very large network with like 8,000 parameters. 8,000 width. Someone could compute that for us. It's many more parameters than we have data points. And you actually beat Gauss-Newton. Since we just looked that up, I mean, the training accuracy is higher. You interpolate the data pretty much, and you have a test loss or test accuracy that's also much better. Okay, you see some overfitting. Okay, fine, but it's not the end of the world. And it only costs you, a bigger network and 100,000 steps of SGD. Fine, nothing. I mean, it's a very different ball game that you're playing. But I think the result is very much as I don't know if this is unexpected or expected to you, but it's really giving you an alternative to working hard on linear algebra and optimization in this case. Of course, going back to Andreas's question, is Gauss-Newton worth it? I think in this case it would still be for me, because I mean these 0.5% in the test loss, I would be happy to take that because it's probably just a statistical error. If I have a network of with 200 weights or so. So if someone asks me for a prediction, I can do this much, much quicker than with this one. But okay, that depends on what your job is here. Yeah, question?
So the Gauss-Newton
Yeah.
Result for the small network.
Yeah.
So the train accuracy here is like really good, almost 99%.
Yeah.
But the test is much better than the Gauss-Newton. But the test accuracy is only 0.5%.
Yeah.
The Gauss-Newton.
I would make a big deal
And
about it.
I wonder what happens if you train Gauss-Newton, you only did 30 iterations.
Yeah.
Here you did 100,000, and the test doesn't improve after 20,000.
Yeah. Yeah.
So if you ran Gauss-Newton for forever,
Yeah.
what would happen?
Yeah, so that's your homework problem. And so in order to beef up the Gauss-Newton, which was not really my intent, here's the one thing you want to do. I didn't add an explicit regularization, like a weight decay, and then you can train it for longer. So I did early stopping here, I think. I stopped at 30.
Oh.
If I went to 100, you would interpolate the data, but you would overfit a little bit more. If you add explicit regularization, now you have a regularization parameter. And if you choose that judiciously, and actually, so Gauss-Newton for me did not get a compute budget, if you realize. One shot. Give the problem, do it, no hyperparameters. Okay, 30 iterations is something I think people who work with me, that's my go-to. Don't want to waste more time, but there's some burn-in that can happen, and then you get it. Anyway, so that's a homework problem. Since you have the codes, it's actually not as hard as you may think. But yeah, I didn't really think about pushing this too much. Because this is a characteristic result that you would expect. But yeah, excellent question. Okay, good. So quick summary, and then maybe we can even look ahead a little bit into the next class, or we do a break early and do a longer next class. So we looked at the two different formulations that I would like you to keep in mind for this course for sure, and maybe even for your work. You have stochastic approximation and sample average approximations, different types of theoretical results, and also very different types of algorithms and numerical behavior. One the SAA works on much more parallel compute, much more linear algebra, efficient ways to. This was a very naive vanilla Gauss-Newton, so you would want to be much more strategic about how to store things, how to get things. So the K-fac will be something very close to that. And then the SA method, where sort of you have some guiding theory about the learning rates, but that was not really helpful, to be honest, because almost like there are still infinitely many sequences, and some work better than others, and the batch size comes in too. So there's like a different ballpark. We chatted just briefly about backpropagation to give you a sense of what it means to do this, especially for the Gauss-Newton. And yeah, then we have a Gauss-Newton in the small regime. Oh, sorry, what am I doing? Yeah, we have a Gauss-Newton in the small regime and the SGD. Really, in the over-parameterized regime, that's sort of where I want us to go for the next 2 optimization lectures, because that is a modern practice. And actually, maybe now already you can see why this superscaling is the trend that we're seeing, at least if you extrapolate from this example. It's a pretty safe bet. So that's why people are interested in it. Some open questions, which we'll get to. We still really haven't figured out why SGD would work so well. You would expect it would overfit. Maybe since yesterday, since we talked about double descent, you wouldn't anymore, but it's still something we should look more into. And then maybe also this role of the noise in the optimization. Like, is it a feature or is it a bug? That is something to look more into, which we'll do in the deep dive that we're doing. So we'll look at implicit regularization. We'll actually look at the weight dynamics in continuous time, and really treating the SGD as a differential equation, and play around with that one. And yeah, then tomorrow we'll do more modern optimizers. So today is really just plain SGD, no momentum, no nothing. But it can teach us quite a lot that we can look at tomorrow. And because the theory is mostly at that part, and then the other part is more ongoing. Anyway, so that's the first part. We are good on time. So what do you want to do? Do you want to take a break now or dive into a little bit into the lecture and then take a break? Anyone have an opinion? Yeah, Akil. Oh, good question. Another homework problem. I just had a fixed seed of 42. Yeah, I didn't do my due diligence. Should have done that. 42, 43 may be different. But honestly, like from my experience, I wouldn't expect too much of a difference there. It's, yeah, maybe the percentage shift of a percent in one's favor, but you will still have a hard time. So what I'm very confident in saying is that for the small network with the SGD, you'll have a harder time finding good parameters. And then this problem should go away when you go large. Excellent point, of course. Yeah. No.
What is the training data was so lower than
Yeah.
test data?
Yeah.
What happens if your first?
Oh, then you're extremely lucky. I've never gotten that lucky in my life. You would always expect to be a little bit in the overfitting regime, because the training data, so it's sort of like teaching to the test, right? So you would always do well on the problems you have seen, but the unseen problems you would have and sometimes okay, what could happen is you have a sort of a slight typo in your code and there is a different scaling that's problematic, but usually that's what you see. Okay, let me check the slider real quick. Oh yeah, okay, go for it. Yeah. Yes. Yeah. Well, very good. No, very good question. So we need to be actually more subtle about how we count parameters, is what you're saying. Yes. Yes. Yeah, that could happen too. I haven't checked for this example. But actually you see that in, again, like large language models is one of the areas where people go very large in the training time. And then later on, they have different versions of the model where they, try to be smart and get some weights to zero, or quantize them away, do low rank stuff, because the inference time compute is mostly what is expensive. Yes, but what I will say that the number of parameters is also too oversimplifying, because there are many ways if you have different layers to add parameters. You can have width there or depth or whatever, and convolutions versus non-convolutions. So yeah, that's another good question. Yeah.
We talked about parameter-wise over double descent.
Yeah.
I've also heard this kind of epoch-wise double descent, where you keep training
Yeah.
for
Grokking.
longer.
Yeah, yes.
But this is kind of opposite of what you would expect early stopping, kind of the classical.
Yes, so there's a phenomenon called grokking,
Yeah, grokking.
which I have not honestly seen in my work. Maybe I'm not patient enough, but it's an interesting thing maybe to put on people's mind, is that this phenomenon that you train, your training loss is zero, and then usually normal people would stop, including me. But apparently, if you keep going for an obscene number of epochs, at some point there's something happening that the test loss suddenly also drops again. Anyway, I haven't been seeing that. If anyone, you have the code, just put in. It should work on Colab. I didn't test that part, but maybe someone of you can do that. Then you can just see if you get into this grokking thing. Would be pretty cool to have an example for it. But yeah, this is another thing that can happen. Okay. Is food here?
Yeah, we're
Okay.
gonna wait a little bit. Because I think the room is blocked until 10.
Okay.
The food, I think, is delivered to the other room.
Okay.
Not there. Also after the second lecture, there will be a group picture. So we'll probably announce it again, but just keep that in mind.